Glad you did that after I was making faces.
And we are now recording, so I'm going to send this right to Dick Krieger now.
Good afternoon, guys. Appreciate your attending again and hope we gave you something of value today. Last week, we had a session on air conditioning where we explained the operation of the internal heat exchanger on our new 1234 YF trainer. And I also discussed the H block, and we lightly touched upon subcooling and superheat. And we'd like to spend a little more time on that today, giving you some further explanations and then some demonstrations on why we feel that mobile technicians working on vehicles should be using this as their one of their diagnostic strategies. It's certainly not new, as I said last week. The commercial and industrial HVAC techs have been using superheat and subcool for years. In fact, most of their specifications are based on those values, not so much like we do. When we fill up a car, we look at the specs and find out how many ounces of refrigerant it takes. And if we put that amount in there, we expect it to have the right amount of charge. Superheat and subcool is a much more accurate way of determining those statistics and also a better way of determining system performance. So we're going to start off by seeing a brief PowerPoint here, and then Rick's going to take over and hands at the shop with our 1234 YF trainer. So today we're going to discuss superheat and subcool diagnosis, using these as a diagnostic routine. Before we do that, I think it's important, and I apologize for text on a screen, but we need 3 definitions to be understood. And the first one is called saturation temperature. And that is a temperature at which a material changes its state, either liquid to vapor or vapor to liquid. And we're going to be using saturation temperatures in our calculations today of subcool and superheat. The second one is subcooling. What is subcooling? Subcooling has to do with a condenser, and it is the amount of heat in degrees that the refrigerant is cooled in the condenser after it changes its state from a vapor to a liquid. We know that refrigerant enters the condenser as a vapor from the compressor, and then it's cooled by the outside air into a liquid. Just like we know that a material can change its temperature without changing its state, and that's what we're doing here. We're decreasing the temperature. On the evaporator, we're doing just the opposite. So superheat has to do with the evaporator, and superheat is the amount of heat in degrees that the refrigerant is heated in the evaporator after it changes from a liquid to a vapor. That's what's going on inside the evaporator, and in doing so, it boils, as we know, and we keep thinking in our minds of boiling as something to do with being hot. One of the things that I used to do when I was teaching, and I would take a mason jar and I soldered in a vacuum pump access fitting to the lid, and I filled it half full of water, and I held it up and hooked it up to the vacuum pump. And of course, you know what happens, the water boils, and I'd ask somebody to come up and hold on to the jar. I'm not holding that, it's hot. I said, no, it's not hot. So we understood these things in principle, but now we're going to use them in diagnosis. So again, summary slide, saturation temperature is the temperature at which anything changes its state. Subcooling has to do with the condenser, the amount of degrees of subcooling. We want to know how much that temperature has changed in the condenser, and the same with the evaporator in superheat. How much has it increased in temperature? Generally speaking, and as we know, saturation temperature depends on its pressure. The boiling point of any liquid or vapor changes with its pressure. Any temperature of a liquid below its saturation point is called subcooled. So that has to do with a condenser. Any temperature of a vapor above its saturation point is superheated. And that's what's going on in the evaporator. Again, summary slide of the three definitions. Are there any questions so far?
Dan Beeson just said that the three things you're talking about could be prep work for the student before to research before a class starts even. So
Absolutely, Dan. That could certainly be an assignment prior to. And by the way, guys, this PowerPoint and the big one that I talked about with 155 slides is available now for you. It's not available on our website. It's too big to send. But if you will send me a request via email, I will send you a Dropbox invitation where all of these documents, including the PDFs, the chart, the two PowerPoints, this one and the one I did before on the H block and IHX, will be available to you.
Dick's email is now in the chat.
An analogy of this concept, you know that water boils at 212 degrees, of course, at sea level at 14.7 psi. If you drink a glass of water at 70 degrees, it has been subcooled 142 degrees. That's kind of wrap your head around this. You're drinking a subcooled liquid because it changes its state. Its saturation point at sea level would be, and when it changes state from liquid to vapor, is 212. So on the air conditioning system, we have the refrigeration cycle loop that we all are familiar with and have taught various ways with. So the superheat, again, has to do with the evaporator, where heat from inside the car is being moved across the evaporator, which causes the refrigerant to boil, grabbing all the heat and cooling off the inside of the car. But that heat is now transferred to the refrigerant. The refrigerant then goes into the compressor, comes out of the compressor into the condenser, and here we are cooling the refrigerant by passing air from across the condenser, which transfers the heat from inside the refrigerant to the outside air. Now, we all have seen the low and high side gauges before, and I just want to spend a second explaining a little bit about, we've always looked at the outside ring, which is pressure. And we all know that, but what about all those other dials inside the gauge? What those are temperature scales for different refrigerants. And you'll see on the gauge, if you can see it up close, you'll see it says R404A, 134A, R22, and R410A. The gauges that you'll have on your AC system will have 1234YF or 134A or even R12. Now, those are scales that any given pressure, you can draw that needle line down to where the equivalent temperature would be. I just wanted to show you here, if I can, on my pointer. Get a little bit bigger pointer here. Let's see. I guess you can see it, but it's on that. So give me arrows here. Here we go. So we have the outer gauge, which is pressure in PSI, and most specifications will call that PSIG, which means pressure per square inch gauge pressure. And then the next one in would be bar. That's the black one. Of course, we need a pressure temperature chart specifically for the refrigerant that we're using before we can calculate subheat, superheat, and subcool. This is one for 1234YF. It's available for you on resources there. And here I've zoomed in on it. So if we had a pressure of 20 PSI on the low side, we're using the chart to create or to convert that to a saturation temperature. So the saturation temperature for 20 pounds of pressure for a 1234YF system is 18 degrees Fahrenheit. Mostly we use Fahrenheit because the numbers are more closely related to each other, pressure and temperature. On the high side, if we had a pressure of 148 PSI, that would equal 110 degrees saturation temperature. So let's just go through a live scenario here. We took screenshots of everything we did yesterday. Here we're hooked up to looking at the high side gauge of our 1234YF system, and the needle is pointing to about 151 pounds. Now we could use the chart on the gauge to equate the saturation temperature, but it's not as accurate as using the chart. The chart is much more accurate because you have increments of pressure and temperature. Here you'd have to guess at the temperature chart for 1234 YF. So using the chart, you see that from the pressure temperature chart, 151 psi of 1234 YF is 113 degrees saturation temperature. Now we need to measure the outlet temperature of the condenser. That's where we need that nice contact thermometer that we talked about last week. Do not try to use an immersion thermometer sensor that comes with your meter. They're not nearly as accurate because the thermocouple is so small. But if we measured 102 degrees, we simply subtract the saturation temperature from the actual temperature and we get 11 degrees of subcool. Now, the documents that I have made for you, it gives you the specifications for most cars. And 11 degrees of subcool on the condenser is a pretty good reading. If we go to the low side, right now we're getting a pressure of 38 psi on the low side. Using the chart, we get 40 degrees of saturation temperature. Now we measure the outlet temperature of the evaporator with our thermometer, and we get 48 degrees. And using the math, we got 8 degrees of superheat, which is again a good reading for this system. Questions before we move on? Make sure that you use a contact type thermometer, and this one in the middle right here is one that is designed to clamp around the tubes coming out of the evaporator or condenser. It's kind of a neat tool. They're not that much money. You can get a good one for between 20 and 30 bucks. And they got the K probe on it. And remember, your K probe can be adapted to your common and volt sockets also with that simple adapter. So why do we want to use superheat and subcool? It checks the efficiency of the airflow across the evaporator condenser. So if you got a condenser all plugged up with leaves and road debris, this method will determine that. It's one of the few things that will. Remember last week I talked about a silver bullet checking the temperature difference between the inlet and outlet of the condenser and evaporator? This is kind of what we're doing here, but it's much more accurate than just measuring the two temperatures. It is the only accurate, really accurate way of checking refrigerant charge. And again, commercial and industrial refrigeration, that's what they charge to. They charge to superheat if it has a TXV or subcool if it has an orifice. Now, let's see this in action unless there's some questions we can answer before we go on.
Mike Hobson asked question, always measured at the outlets?
Yes.
Condition and evap?
Yes, the condenser and the evaporator measure the outlet temperature coming out of both of those components. Let me end my show and discard, call up my screen here and stop sharing, and I'll turn it over to Rick and Kevin.
So I need Kevin to turn on his screen share or do his camera.
Camera's on, Rick.
Okay, I got to get you into the picture here somehow. Talk some more so it'll actually switch. There we go.
Okay. There we go. Yep, we got you.
Okay. So now I've pinned Kevin to the screen. Hopefully you're all seeing him, or not yet. You have not.
Got to share your screen there.
Yeah, there we go.
Now we see the PT chart.
And then there's Kevin.
There's Kevin. Okay, great.
Okay. So it'll be a little blurry as Oh, wow. This worked so good about 10 minutes ago. But anyway, I think what happens is as we get more and more people involved in the call, we get a
Affects the
degradation of
bandwidth. Yep.
quality. Yeah. Apologize. So we're looking at the trainer we had the other day, where we've got temperature and pressure gauges mounted right on it. And what we're going to be doing is doing a live demonstration of this. So what Kevin's going to do for us right now is give us some numbers, and so we can do the calculation. The PT chart is available in the chat window as a picture if you want to look at it, but I've got it here. So right now I'm going to ask Kevin to give me low side pressure and temperature of the outlet.
Okay, low side pressure is around 34 and temperature coming out of the evaporator is at 43.
So the 34 PSI will translate over to around 35 degrees.
That's your saturation temperature.
That's your saturation temperature. And so if we do the 43 minus the 35, we're going to get 8 degrees of superheat. So we know that the TXV on this, the H block TXV, is that the spring in it is set to give us around 8 degrees of superheat. And now if we look at, sorry?
What if it was 15 degrees of superheat?
There could be the possibility that that's where it's set, or another indication is that if it's not within its set limits, we usually say that TXV should be in that 8 to 12 degrees of superheat, that it's usually an indication of a low liquid level in the evaporator, meaning that we're adding too much heat, we're getting too much vapor, and we're getting lots of superheat.
And just one point, I want to add that the superheat for a TXV is different than the superheat for an orifice tube.
Oh, Kevin, you're taking us on a ride.
Dick, why is that? Why is it different?
Because we use an orifice tube evaporator is called a flooded evaporator, and we want like what 0 to 4 degrees, 0 to 6 degrees of superheat in an orifice tube evaporator. Is that pretty close?
Yeah. And the other thing that we have is with a orifice tube system, we have an accumulator, which works as a final evaporator. So the accumulator is going to ensure nothing but vapor goes to the compressor. In a TXV or H block TXV system, it's the TXV's job to make sure that liquid never hits that compressor. So that's why we need the superheated vapor.
Or the IHX.
Yes, the IHX also helps with that. Now is the IHX unit is going to add some more superheat. And then it's also going to further the subcooling as we discussed the other day.
There's a request if you can repeat the orifice evap numbers.
Okay,
it is both of those are in the handout or the document that I put together. But orifice tube is 0 to, I think it's 4 or 5 degrees range. And the TXV or H block, remember that an H block is nothing more than a TXV without the capillary tube. So, Rick, what are your normal numbers for a TXV?
Usually in the 6 to 12 range, and these are all Fahrenheit degrees again.
And what was the superheat temps of the orifice tube system again?
0 to 6 degrees, I'm going to say.
Yeah.
Thank you. Those were all questions in chat.
Yeah, no problem. And again, that's in that PDF document I put together, and I will send to anyone wishing a copy of all of those.
Richard Smith says, on a hot summer day, can superheat be increased?
Yes, if you have a high heat load, there is a chance that you're going to see more superheat. It comes down to the evaporator's ability to, the amount of liquid that it can hold. So there are really hot days when you might see higher superheat numbers. But most systems, well, in the past, a lot of systems were over designed because we had lots of horsepower to share. to make the thing work. But these days, as we talked last week, we're really going for high efficiency. So we might see, big differences in that. Some days it's just going to work really hard and you might get more superheat than intended.
One thing I might add that I forgot to mention, before you check superheat and subcool, the system has to be stabilized. So it needs to run for 10, 15 minutes before you actually make these measurements. And the system needs to be running at a stabilized state.
Peaking of 10 to 15 minutes, you got 10 minutes.
Okay. So let's do a live subcooling now with this unit. So I'm going to get Kevin to give us the readings for outlet of condenser and high side pressure.
Okay, so the condenser out, I have 106.3 degrees, and I am at 155 psi.
So again, back to our chart, 55 psi goes to 114 degrees Fahrenheit. So we got 114 minus 106. So again, we're in that 8 degrees of subcooling. Now, one of the things that's happening with this unit right now is the numbers the numbers will always work on this machine, but because we got evaporator and condenser so close together, they do affect each other a little bit. But again, it's just a learning moment. And the other thing right now is we've got all the fans cranked to the max on this. So that is affecting numbers a little bit too. We're going to get variations with that temperatures based on fan speeds.
And the nice thing about this trainer,
Sorry.
Nice thing about this trainer is that we can vary the fan speeds on both the condenser and the evaporator to create the same situation as though a restricted airflow, and the subheat and supercool will respond accordingly. So you can duplicate adverse conditions using both the restriction valves and the fan speeds on our trainer. Sorry, Jimmy, I didn't mean to walk over you.
I'm sorry. I also. So Mike Hobson was asking, are you saying that these numbers should be the same regardless of ambient and humidity?
Yes, because it's going to work, the temperatures will vary based on ambient and humidity, but it will also have an effect on the pressure. So again, the spring inside the TXV is what controls the difference between the temperature of saturation and the amount of superheat.
So the numbers will go up and down, but the range of the superheat and subcool should be the same.
And it's when you fall out of the range is when you can start using this as a diagnostic. So what I'm going to ask Kevin to do right now is we're going to create a restriction to the evaporator. So we've got a valve on this trainer. The red valve controls the liquid level coming from the condenser. So I'm going to ask him to partially restrict that, which is going to reduce the liquid level in the evaporator. Now, what we have to do is we got to wait a minute, but what Kevin could be telling us right now is what's going on with the gauges.
Okay, well, on the low side, my pressure is going way down. My temperature out is at 43.5 right now. My pressure is almost at 0. Maybe I created too much of a restriction here. Yeah.
Okay.
Just a little bit. So I opened it up a little bit more. So I'm at around 25 pressure.
Okay. So 25 psi is 24 degrees.
And my temperature is going up. My temperature out.
And what is it?
I'm at 50.7 right now. But I'm almost at, I'm at 35 psi at 50.7.
So 35 psi is 36. So we're getting up in the 15, 16 degrees of superheat. So we've got more superheat than designed, and it's due to the low liquid level in the evaporator. And we know that it's a low liquid level because we created it. And if Kevin was to open that valve back, it will normalize and come back to where it was before. Now, one of the other things we're going to do quickly is reduce the fan speed on the evaporator down to lower level, which is now going to reduce the heat load on the evaporator, and we should see it fluctuate the other way.
I have the fan speed on 1 right now.
Yeah.
Joe Hart says, what will the numbers look like for an overcharge?
You'll see virtually no superheat in the evaporator. The numbers
so right
lower
now my
than
pressures drop down to 30, 32.
And your temperature?
Right now it's at 41.5.
Let's give it one more second and give me the numbers one more time.
Okay, I'm at 32 and 39
32
PSI.
and 39 degrees. So 32 PSI is right around 33 degrees. So we're still in our range of 6 degrees of superheat. So even with a low fan speed, we've got lower temperatures, but our superheat's still there.
You want me to turn the fan off, Rick?
If you turn the fan off quickly, and that'll probably be our last demo.
And I just want to point out that when you make these measurements, both pressure and temperature, they should be as close to instantaneous as possible because they're changing. So don't read the pressure and 10 minutes later read the temperature. Try to do them both at the same time.
Yeah. So remember to turn the compressor or the bypass switch on there, Kevin.
Somebody asked what happens if the cabin air filter is clogged.
Typically, it's going to reduce the amount of airflow over the evaporator, and you're going to see low superheat.
And another question, are the numbers lower for overcharge and numbers higher for undercharge?
Yes. When you're dealing with superheat, yes.
The document that I have prepared gives conditions, causes, and effects of high and low superheat and subcool, different things that will cause that.
So, Kevin, what are our numbers now?
I'm at 28 PSI, 34.3 degrees Fahrenheit coming out of the evaporator.
So 28 PSI is 28 degrees, and we're at 28. So we've got virtually no superheat because we're not evaporating the liquid in the evaporator. So there's a condition of what happens when there's little to no airflow across your evaporator. So if it freezes up on you, it turns into an ice block. Or if you've got dirt in it, or some kind of science experiment with stuff growing in it, or a plugged filter. Those are what you can expect to see.
So right now I'm at 20 PSI and 29 degrees Fahrenheit.
Yeah. Okay. All right. So I will stop sharing this. So within our documents, like I said, in the chat, you're going to be able to find, there's a picture of this chart that we created a couple of years ago when we first started doing this. We were having a hard time finding one, so went and gleaned some information and found one. It works well for this. There is a picture of it, like I said, in the chat that you can grab, or it's in the resources that we have as well too.
Several of you have indicated you'd like the link to the Dropbox. If any of you want all of these documents, including the mega PowerPoint, just let me know and we'll send it to you. Just make sure that you remember that whatever system you have, you must use the relevant PT chart for it. The one we use today would not work on a 134A system. The concepts are the same, but you need the chart to match the refrigerant.
All right, I am stopping the recording, but that doesn't mean the education stopped.